Okay, so this is a problem about the volume change of the balloon. So there's a balloon, and we know the volume, 25 liter, and 353 Kelvin. Okay, so we know the volume, and also we know the pressure, and the pressure unit is kind of interesting. So I want to change that into the ATM. So divide this one by 760 mmHg. That will make me 3.39 ATM. So I just like this ATM as a pressure. So this, I know my volume and the pressure, which is 3.39 ATM. And then now you change into the different pressure, 1.35 ATM, and the temperature is 253 Kelvin, and they want to know what is my volume. Okay, so let's say what is my volume for that. So what is remain fixed? So in this case, the number of moles here is the one remain fixed here. Okay, so we can say we know PV equal nRT. In this equation, we can say nR, which is a constant term. So PV over T is a what remain constant. So in this case, pressure 3.39, volume 25 liter, temperature 353 Kelvin. And the pressure 1.35, volume, what we want to know, and the temperature 253 Kelvin. So therefore, your volume is 353, 3.39, 25, multiplied by 253, divided by 1.35, that will lead me 45 liter. So answer for this is C. So second one is essentially average speed differences, which is called the effusion problem. And we have a methane molecule. So methane, and you need to know the chemical structure. I think this is part of what is required. So methane is CH4, and that corresponding to 12 plus 4, it weighs 16 grams per mole. Right? So that's the weight of each molecule. And the other one is argon. And using the symbol argon. And if you look at that, argon is 40 grams per mole. And as you know, the same temperature means same kinetic energy, and kinetic energy is half mv squared. So because both of them has the same kinetic energy, so half of m1 v1 squared is half of m2 v2 squared. Let's say one here is methane, and 2 here is argon. And what we'll say is 631 meter per second. That is, they know that V1 is 631 meter per second. That's for the methane. Now question is, what is V2? The velocity. So if you're looking at the original equation, you can easily cancel this one out, and essentially V2 over V1, velocity ratio square, is same as inverse mass ratio, which is M1, M2. So here I will say V2, which is argon, and then this one is 631, that's the square. N1, which is that's methane mass, which is 16 gram per mole, and then M2 is 40. So V2 is essentially square root 16 over 40 times 631. And if you do that, you will get 399 meter per second. And that's the closest one is this. So the C is the right answer. Okay, so this is a question about, let's say, using the ideal gas law. There's one syringe containing, our volume and the temperature and the pressure. So from here, the first gas is carbon monoxide, but we can say first kind of gas, N1, can be calculated, right? And the second syringe is this is a volume, temperature, and the pressure, and then N2, second number of moles of gas from that syringes can be calculated. Okay, so each one, the gas has this amount, and the second one containing this amount of the gas, and then now you both are being injected into a container whose volume is 1.0 liter, and the temperature is 273 Kelvin. And then now what will be the final pressure, right? The final pressure should be nRT over volume. In here, N is coming from N1 plus N2 from these individual syringes. So let's figure out what is my N1. N1 is PV divided by RT. So we just have to put that the right numbers. The pressure 1.2 atm, good. Volume milliliter, so I just have to use 0.589, that's a liter. 0.082, that's a gas content, atm liter base, and the temperature is 325. And if you do that, you'll get first one is 0.0265 more. Okay, what about the number 2? The same, PV equal nRT. So RT, if I do that, pressure is 2.6, volume in liter 0.473, and R 0.082, and the temperature is 298, and that will give me 0.0503 mole. So combining this together, I will get N, which is a sum of those, 0.0768 mole. Okay, so this is the number of moles of the gas going in the container. And what's my temperature? It's shown up here, 273 Kelvin. What's my volume? Actually 1.00 liter. So, and then R is same as usual, 0.082. So therefore, the final pressure is 0.0768, 0.082 multiplied by 273 divided by 1.00, and that will lead me to 1.7 ATM. The answer is for C, 1.7 ATM. Okay, so this is the last question, and well, the question is, which one has the lowest density at standard temperature and the pressure? So density, once again, density is mass for volume, right? So for a given 1 moles, you will have the one with the lowest molar mass is the one will have a lowest density, right? Because if your molar mass is essentially mass per 1 mole, so if you think about giving that 1 moles here, each mole will have 1 mole will have a same volume. Do you remember the hydrogen versus helium? Hydrogen is 2 grams per mole. Helium, Hindenburg, which is 4 grams per mole. So this is a lighter, because their molar mass, this is a lighter gas, lower density. So the lower density means lowest density means lower molar mass, and this is essentially they have a same kinetic energy, and because the mass is small, kinetic energy, which is a half mv squared, so they are the one fastest moving gas, right? So corresponding to lowest density now is the fastest moving one. Which one moves the fast? A is the one that moving the fast. So therefore the answer for this is an A. Okay, thank you for your attention, and good luck with your third exam. Bye.